Yeah, please, please. I've been waiting for you.
Okay. Good afternoon, all of you, for the session 13th of the ATAL FDP program. On behalf of University Institute of Technology, RGPV Bhopal, I welcome you all for this session. Our expert is Dr. Nilima Satyam. I welcome you, madam. Uh, Dr. Nilima Satyam
Thank you, Arun.
is currently working as an associate professor in Department of Civil Engineering, Indian Institute of Technology, Indore. She has completed her PhD and MTech from IIT Delhi. She worked as an assistant professor in Earthquake Engineering Research Center at IIT Hyderabad before joining IIT Indore. She is actively engaged in the teaching, research, and consultancy in the field of geotechnical engineering, particularly in geotechnical earthquake engineering, microzonation, and site response studies, landslide hazard and monitoring, microseismic data processing, and rock engineering. Dr. Nilima has received the research grant from DST, MHRD, AICT, ITRA, DAE, NIOT, NRDMS, and ISRO. She has published nearly about more than 150 research papers in national and international journals and various conferences. She has been a chairperson of the selection committee for Next Scholarship in Japan since 2015. She is also a recipient of the various awards like the Best Research Award at IIT Indore, the CIDC Vishwakarma Academic Award from the Construction Industry Development Council from Government of India and Construction Industry, Overseas Famous Scientist Project from Ministry of Science and Technology, China, for visiting the Shangyo University. She is also a recipient of Career Award for Young Teacher from AICT, Young Engineers Award in Civil Engineering Discipline from the Institution of Engineers, Kolkata. She is also a recipient of Young Scientist Research Award from BRNS, Department of Atomic Energy, India, and the Young Woman Engineer Award from INWES International Network for Women Engineers and Scientists. She is also been a recognized member of the various editorial boards of various journals and also member of professional societies like the Engineering Council of India, the Indian Geotechnical Society, the member of International Society of Soil Mechanics and Geotechnical Engineering, and European Geosciences, and many more. And her research areas are, like I have already discussed it, like geotechnical earthquake engineering, dynamic soil structure interaction analysis, liquefaction hazard and mitigation, environmental geotechnics, landslide research, and rock mechanics and underground structures. I welcome you, madam. Today's expert talk of madam is on seismic soil structure interaction analysis of pile raft supported asymmetrical buildings. I welcome you, madam. Over to you.
Yeah, thank you, Dr. Aruna. I hope I am audible, right?
Yes,
Yes.
madam.
Sure.
Yes.
I'd like to share the screen. So thank you so much for the introduction. And so as Dr. Aruna mentioned, my topic is on SSI, especially the dynamic soil structure interaction, and which we have carried out for a pile raft structures, which is supported for asymmetrical buildings. So this is actually why we are working on asymmetrical structures, because asymmetry, either geometrical asymmetry or load asymmetry, is something which is very, very common these days. People are like, most of the times, when any structure comes for wetting, I observe that, architects are doing everything and kind of thing with their fancy sort of things. A lot of, asymmetry has been involved in the structure rather than giving the issues of stability into consideration. So asymmetrical structures are more, vulnerable, like, so that's why, not much research has been considered, and this is part of my PhD students' work. So I'd like to start on that. But as I said, like, we are working on the how the interactive effect of the soil, because soil is, this is actually the DSSI, right? Dynamic soil structure interaction. Soil is a particulate material, granular material, highly nonlinear in during the dynamic load. So how the interaction of this soil with the substructure, here my substructure for consideration of this particular research topic is pile raft, because pile rafts are also considered to be one of the very effective and economical foundation system in the recent years, because piles can be a very good settlement reducers, and raft can be a major load bearing element. So the combined advantages of both raft and the pile can be achieved by designing a pile raft foundation system. So this is the outline of my talk for today. So I'll be giving the brief introduction of the problem along with that literature, very short. Okay, and then this part is our major part where like we have developed our own numerical model for implementation of this complete DSSI for asymmetrical structures. In the sense here, what we have, the complexity of this particular problem is we have a soil to be modeled, we have a substructure, and you have a superstructure, which is asymmetrical building. So all the three things have been incorporated, and interactive effect of soil, substructure, and the superstructure has to be understood and studied. So then like anything, when you do it, either numerical especially, you have to have a validation. So we did the validation of our numerical model, then we applied that for other parameters of dynamic soil structure interaction to understand which parameter is more controlling effect and something like that. So with a brief conclusions, if I talk about the DSSI, see, it is actually many times, in the industry, especially people feel as a myth, carrying out SSI or DSSI analysis is very costly, I think, something like that, or it may be overestimates the project cost, etc. To be frank, we are going to evaluate what is the response of the complete system when you take the interactive effects is something which we are going to do that. So in this context, so what we have done is like we want to understand this. As I said, like soil is such a non-linear material with a lot of other issues, like you have a resonance effects or damping in soil in structures. When you do analysis, you consider damping as 5%, right? But what about the damping in soil? So damping in soil, especially in the lateral direction and vertical direction, are exactly very, very different. You cannot have a same damping, so because this material is very, very challenging material to handle it. Many times, why people underestimates the geotechnical behavior of the substrata is because they cannot understand. That's a problem. They cannot evaluate or quantify the response of my soil. So when you cannot understand a person, what we do? We generally ignore, right? Him or her. So the same thing we do with the geotechnical engineering as well. So the major important factors which influence the effect of SSI are impedance contrast or the resonance effect, damping, and stratification. Because the stratification, generally soil is not homogeneous in the state real field, it is always like stratified, and this stratification makes the things more complex. And method of analysis, how do we do it? Like we can do in majorly two approaches. One is like direct approach, and another one is substructure approach. In direct approach, we model everything as like superstructure, substructure, and the soil as completely into one unit, and then we do the analysis. In substructure method, what we do is like we take this foundation embedded in substrata, that is the soil, and then do the analysis. Whatever you get the response on the top of at the foundation level will be given as input to our superstructure. Many times in the industry also, what happens, people consider that fixed base condition. How can you fix as a superstructure to the ground? Because ground itself is dynamic, right? It's always under microdynamics. Ground is not static. You may not be able to feel it because we are not able to be so sensitive to that vibration, but ground is always under some micro vibrations. Okay, so you cannot fix it, right? Until unless you go very deep and anchor it very strong, even then you cannot have 100% fixity at the foundation level. So this is something which we have to understand. There is nothing like a fixed base analysis. So anyway, so then significance system can be modeled nearest to the reality, so that it's not like always overestimate. Many times if you do the exact evaluation of the complete response of the system, you can even save a lot of money. And that's actually the myth that's there with the industry. And because it gives you accurate response of the complete system or the elements of the system that is involved, like soil, substructure, and superstructure. And since you can get the actual reality or the response in terms of response of the overall system, so you can have a better safety and the serviceability of your superstructure. So let me show you some of the past damages during the classic earthquakes that happened in the different parts of the world. So I'll start with the Mexican earthquake, which happened in 1985 with a magnitude of almost like 8. So there is a lot to study during this kind of damage or forensic analysis of after an earthquake or any disaster in general, because it gives you a lot of information in terms of damage pattern. So when you say damage, it's not about the damage intensity. We also have to look at the pattern, the damage pattern. So damage pattern can be, it gives you a lot of information. So if you see here from this particular earthquake, 10 to 12 story buildings, which are on, soft alluvial sort of formations or soft clay formations, whose period was increased about 1 second, okay, for the fixed base structure to almost like double when we consider this SSI analysis. So most of this, you can see here, this is like something like a L-shaped building. So these top floors, they fail due to inertial effect. So you can see the soft story collapse here again. So this was sort of the damages, and this is a classic damage picture. You can see here, this is a Hanson Expressway. Almost like, this picture is very classic. You can see part of this expressway is intact, but part of it completely collapsed. You can see why the damage intensity and pattern is so different within few meters. It's not even 800 meters away. So within this 800 meters or maximum 1 kilometer, the response is very different. It has been designed with the same kind of POs and foundations, right? But why the response is exactly different? Yahan pe intact hai, and yahan pe it's completely like complete damage, collapse. So this is actually the damage, especially the behavior of the soil is under dynamic loads is very site specific, and the soils that behaved, however, whatever way they behaved here, were not behaving the same here, because the soils are highly heterogeneous both laterally and vertically. So in this perspective, if you look at it, the damages or the damage pattern intensity is also site specific. So let's see our own classic example, which is an eye opener in the country. That's a Bhuj earthquake, happened in 2001 in Gujarat, and 4-story L-shaped building, in Ahmedabad, which is almost like 200 kilometers from the epicenter. The damage intensity or the damage was much higher when you compared to the structures that have been near in Bhuj area, near to the epicenter. The reason behind is like more of asymmetrical structures have been built in Ahmedabad, and there was a far field effect. As per our laws of physics, when a seismic wave travels, far distance, it should die, right? But it's not same always. It will die or reduce the energy when it passes through the soil. There is something called amplification, or like site amplification, we'll say that. And the wave is interacting with this kind of granular particulate soil loose strata. There is a chances of the wave amplification when it's passing for a longer distances. So that's what is called as amplification. So far field effect, we say, then the wave is traveling for far distance, like the laws of physics are not applied over there. The wave is not dying, it's increasing, it's gaining the energy and increasing the amplitude. So when the higher the amplitude, obviously there will be much damage. So these two things have been observed in Ahmedabad, where there was a site amplification happened because the soils have been very soft, and far field effects have been occurred. So another 10-story C-shaped building, this is that tower, okay, so has been collapsed. Another very recent one where we can see very distinctly the effect of DSSI is in the Kathmandu Valley, where like you can see the complete collapse of a school building, which is C-shaped building, soft story collapse, okay, of a framed structure. You can see how the foundation failure happened here. Okay, so see this one. Okay, these are about the superstructure part, right? Let me go to the substructure part. Let me see how the pile foundations are behaving during earthquakes. Don't think that these are columns. These are the piles below the ground. What happened to the soil? That is embedded. So it has been completely washed away. Okay, so there's been like the soil has been completely liquefied, and there was a lateral spreading. So that means like material has been washed below the ground. Okay, so the soil has been laterally spread. So because of that, the piles, these are the foundations, they have been like collapsed. And you can see here, this is, you can even, gap formation during dynamic loads. Like obviously there will be a vibrant vibration. It's not in x direction or y direction, right? It can be in any direction, because it's very, earthquake doesn't go in only x and y directions, right? We consider it into in a the three-dimensional frame because we want to do the analysis. But otherwise, earthquake happens in almost all directions in the different amplitudes. So there is when after the earthquake, this rate of gap formation between the foundation, the pile foundation, and the substrata. So when the gap formation, how do the load transfer happens? Because there is only contact on the only 50%, right? The pile is in touch with the substrata or the soil surrounding only 50% of its surface, right? Side friction. So when 50% there is no contact, how do that will transfer the load? So obviously that pile has to be designed in such a way that in seismic loads, even if pile gap form, so you have to consider that so that the structure will not fail. Okay, and this is the structural shear failure of the pile at the connection between the raft, etc. So there is an inadequate connection. This is something which is people ignore this. Okay, so with this problem statement, what we have done is like we developed our own numerical model. Okay, so DSSI for carrying it out. So what does this do? So once you define the complete geometry of your piles, okay, and superstructure everything, it create a mesh. Then assign, you have to assign the material properties like concrete or soil properties, everything, and then defining the boundary conditions. So then we give nodal loads and define the interface nodes and the pay, because there's always an interface element when you talk to the soil part of it. Why? Because I'll just go. So when you have a pile embedded in the soil, okay, and the material that is just adjacent of this particular pile foundation, which we model as an interface element, okay, maybe the density must be higher if it is a driven pile. So and and other properties of the soil will be different. So this is the soil properties, interface properties, and the substructure properties. So you have to consider that. Most of the people don't consider that interface element, so which we have done that. And then we have to define the time step. For each time step, it calculates the response at different nodes, and then it will try to converge the response and to give the final response. So this is actually the overall view of the what exactly the numerical model do that. So this is actually the crux part of it, that is analysis part. So what it do is like the algorithm, it updates the acceleration, and then of course the velocity and the displacements are calculated accordingly. Then it will check whether the element is in contact or not, okay, with the nodes, with its contact nodes. If they are in contact, then it will calculate the contact displacements. Okay, if it is not, then again it will recheck the another problem. Okay, so that is how the actual algorithm work for its analysis. Okay, next one is like coming to the model details. What we have done, we have considered 8 nodal brick element for foundation part, that is for the raft and pile, and of course for the soil. Then 2 noded beam element for beam column, and of course for the superstructure elements. So contact, node to node contact for the column and the raft that's joined. So columns are embedded in the raft, which we modeled as a rigid connection. And the soil boundaries, we consider the absorbing boundaries. Why? Because earthquake, the seismic wave can come and hit my substructure in any direction, right? So, but in our analysis, that inclination of the seismic wave was not considered in this particular analysis. But what we have considered is like the seismic wave is coming and hitting it in a horizontally. Okay, so and then when it is passing, it passes very fast, and you have to model the soil at least like 200 times of the width of your foundation. It's a larger soil model as per the soil sector interaction modeling issues. Then the wave may not come back, right? Because we have to have a observing boundary because it passed through. So that's why we have taken that. Then what are the things that how this program works? So we have to input the data in a very simple way, like .txt file with all the geometrical details, nodal and element details, contact details, boundary conditions, material properties, constraints, load details, and of course, it will give you output data with displacements at different nodes, including stresses. And for graphical output, we use LS Dyna so that we can, prepare it properly. So after we have done or complete this numerical model or developing the code, then we have to do the validation. So what we have done is like we try to do the validation with already published literature, and this Hokumabadi, he has done extensive work both analytically and experimentally and numerically. So what he has done is like he has done the scaled down model test, and these are the properties of like for DSSI. But this is for, he has done it for symmetrical structure. So but we want to use it, our code can use it for asymmetrical or symmetrical, that doesn't matter. So symmetrical is much easier for it. So what we have done is like we have taken his data, this is the same data, so that we can compare our results with our model. So this is the data that from his thing. And so this is a scaled down model where he has run that shake table test, etc., for understanding this. And he also done using a commercial software. Okay, so this is his model which we also done. And these are the three different ground motions he used for his shake table test. So 94 Northridge earthquake, 95 Kobe earthquake, and 1940 El Centro earthquake. So for these earthquakes, he tried two different peak ground accelerations of these particular classic events. He has done the analysis both numerically and experimentally. So we use the same data and the same input ground motion, and we want to see how our values are compared with the already existing literature. So this is actually from this experimental study. This is our numerical part. This is his numerical, which he has done with the commercial software Flag 3D, and this is our numerical model. So our results were being very much closer, okay, with a very less percentage. I can show you the percentage of difference that we observed with these two. Okay, these are the lateral displacements which we compared with a numerical model, that is a flag. So when we compared with both experimental, this is experimental results of his work, so three different earthquakes, and then numerical model that is using flag, and this is our study. So when we see that the percentage deviation was almost like around 10 to 17% when we checked with compared with experimental, whereas with the numerical it was like less than 8%, which is much better. So then, after this validation, we want to do our actual study for considering how the behavior happens for a pile raft supporting the asymmetrical structure. To start with, what we have considered is like we have considered three different kinds of asymmetry, that is geometrical asymmetry, L shape, C shape, and T shape building. And of course, with the same plan area of a standard rectangular structure we have considered. We design like how normal design comes. So we design the foundations and complete structure of all these three different type of symmetrical structures with along with the standard rectangular building. So then we have started, this is actually the data for superstructure. This is the unit weight pile raft, okay, for the concrete part, and whatever the friction angle, Poisson's ratio, shear velocity that we have considered, damping. So with all these material properties for both linear and non-linear, because for soil is highly non-linear, we have to consider the non-linear analysis. So we have done the history slew for it. So for non-linearity, soil non-linearity model. Then for analysis, we have started with our own classic earthquake, that is a Buzz earthquake. So since if you give the complete time history of this Buzz earthquake, the analysis is taking so much time. It was even running for 4 hours, and to increase the efficiency of our time, reducing the time of the analysis, what we have done is like we have taken only the part of the ground motion which is more critical. Okay, so we chop the remaining part. So this is the most critical part of the ground motion with highest acceleration. So that part of almost like 15 seconds we have considered, so that we can input this as a input for the analysis. This is the model for us, finite element model for general pile layout for the L-shaped building. These are all been designed actually, the pile dimensions, pile spacing, everything we have designed for the considered loading system that is coming from the superstructure. And this is for the L shape. Similarly for other two shapes of T and C also. So you can see this is for the T structure, this is for the C structure. We have designed the foundation part first. Okay, then we have started with the analysis. The first one we want to see whether, like, generally people do, right, with the this fixed base conditions without considering the effect of SSI. So we started with, like, what is the effect of SSI when we have the different asymmetrical structures and in terms of its displacements. So first one, like, obviously there was a difference of the response. Then, as I said, this is a 10-story structure we have considered, because we are not worried about, in India, high rise is a term which has no definition, right? We can't define what is high rise. In high rise in Hyderabad is not a high rise in maybe Indore. So whatever it is. So this definition, it's actually qualitative. So then what we have done is, like, we have considered 10-story structure only uniformly for all the asymmetrical buildings to understand the response. So we started looking at different nodes at different story level. What is the response? Especially, mostly we looked at the response in terms of displacements and the stresses. So to understand the effect of asymmetry, we try to compare these asymmetrical buildings with the standard rectangular building. Okay, and started at different nodes to understand which is the most critical node. Okay, so with respect to its response, and then again compared the other two also at different story heights, 0, 3, whatever, it's different story heights. At different nodes, we started looking at the responses. There's so many graphs which I cannot show. Okay, so then we understand which is the most critical node. Okay, so in this particular type of asymmetrical buildings, that is L shape, we found this is the most critical node because of accumulation of the stresses at this particular node. And then, this is at the superstructure response. Similarly, we have to look at the response at the foundation, that is the raft part and the pile part. And pile where? Along the pile length, somewhere in top, somewhere at the bottom, pile tip, and somewhere in the middle. So then we have started looking at the response calculations at the pile in almost all the 3 directions, and this is the pile settlement for different asymmetrical structures considered C, T, and of course L. Then response of the piles. So this is the pile response, especially in terms of, displacement. As I said, like, pile response, we started looking at top of the pile, bottom of the pile, and somewhere in between the pile. So this is the lateral displacements of the pile for C building, C-shaped building, and similarly, this is the pile settlements. So when we want to see the comparison, because there's a lot of, different nodes at different story heights, we got a lot of, responses, different things to compile it, to understand what is the effect of it, and comparing with the rectangular building CLT shapes. And this is a superstructure response, XYZ direction, peak pile response, okay, in X direction, pile in vertical, and of course the raft in displacement. So for all these comparisons, we try to see how is it responding when we take it to rectangular building as our standard for comparison in terms of asymmetrical. So mostly, if you see here, the superstructure responses are like this. So based on this first analysis, what we understand is, like, our code is quite effective, and because it could take all the information, especially the non-linear ground response analysis has been considered, and interface element was being modeled, and we have considered actual design of the complete foundation system, and of course trying to see the response. So our code was been very complex as well, and which can incorporate all this non-linearity in this modeling. And our validation with the existing published literature, both with a commercial tool, that is FLAC, and of course with a scaled down experimental model where the previous researcher was giving us very good comparable results, which is like with a less percentage of errors. So then we conclude that our model for DSSI code is valid method of simulation with sufficient accuracy and acceptable limitations. So then what we did is, like, we as I said that it's for each model, it's taking so much time to run. The computational time was very high in the starting, so we want to increase the computational efficiency of the code. So initially it was taking minimum around 90 to 100 hours so for each model. And because we want the response evaluation at different nodes at different story heights. So to improve the computational efficiency, what we have done, only the part of ground motion of the bus was considered. That is one thing. And of course, in addition to that, we also have done some more things which I will be discussing in my future slides. So then Based on the first part of the analysis, what we understand, the displacements are higher when the interaction effect is included in the analysis almost in all the directions of X, Y, Z. And X response is found to be more, about 20% maximum in case of DSSI analysis in, again, all three directions. And this response, this difference in the response is lesser at the lower levels of the superstructure, that is, which is 2 to 5% and 15 to 20% at the maximum. So when we look at what is the effect of asymmetry in the structure, superstructure, so we found that rectangular building, that response is much lesser than the other asymmetrical buildings, especially the C, whereas it is much higher for L and T. So that is one major asymmetry. Even if you want to go for asymmetry, which one to go for it? Either C, L, or T among the three ones. So C is much better when compared to L and T. So T is giving higher responses, higher because of its whatever shape asymmetry. And then the foundation lateral displacements and the settlements is nearly same for all the structures under the same earthquake load. This is one of the major observations we can make it up. So because here it is actually how the substrata or the soil is interacting with your piles. Okay, so it doesn't make much of the difference when you talk about whatever the superstructural asymmetry. So from here you can say that geotechnical hazard is completely controlled by the substrata, whereas structural hazard depends upon it's more controlled not only on the whatever the response from the soil and the foundation, it also depends upon how your superstructure has been designed in terms of asymmetry. As I said, to improve the computational efficiency, see, we have some n number of piles have been designed. So to do that, what we have done is we applied an equivalent PO method proposed by Paulos, wherein that all these piles you can model it as a single pile. Okay, that's what is called equivalent PO. There is a procedure to calculate the dimensions and other properties of this equivalent PO. So this is one of the established way of doing the analysis, especially for the equivalent peer method. So we applied the EPM because rather than modeling these many piles, if you can model one bigger peer, so your computational time can be reduced. Okay, so that's the idea. So in EPM, how to see, if I just take one asymmetrical structure, L shape, so there may be n number of piles participating in this particular area. I divided just into three different equal parts. So all the piles can be replaced within one equivalent larger peer. Similarly, another one for this area, another for one. How do you know that you have to divide this into three parts? You can make it two parts also, right? I can make all the piles which are so contributing in this area as one single peer and another one is single. So this can also be. So how to do which EPM? Because there is no proper exact guidelines how to divide this into different sections or the different parts so that you can have different peers. So we have made 4 different EPM methods which to understand which one, why this only, we don't know, right? We have to model it and understand which one will be much better. So this is the third one. Okay, so we have done this as third. So we have divided equally like this, okay, diagonally, and then made into 2 POs, and then one is finally everything. Okay, so complete area has been considered. So EPM 1, 2, 3, and 4. For all these 4, again we have done the analysis for, again we started with the L-shaped building. You can see here there are 3 POs here, and there are 2 here. There is only 1 here which is contributing. Okay, equivalent contributing from all the piles that have been there. So for all these 4 EPMs, again analysis has been done to understand the response at different nodes at the foundation and at the superstructure part. So again, this is the X displacement. So as I said, this is the critical nodal point. Displacements observed that particular node was much higher at almost all the story heights, and peak system displacement in principal direction with different EPM models that has been considered is like this. When we consider complete all piles, this is actually the response. Okay, all as it was done in the previous. So when EPM 1, 2, 3, 4, this is the response in X, Y, and Z directions. So based on this, we try to understand which EPM has to be adopted for future analysis so that the computational efficiency can be reduced, because it's taking so much time. You cannot run more model analysis so that you cannot understand. So that's why we came up with this CPM approach. Okay, when we see this is like like 2 to 13% in the first one, and then this is 3 to 11%, and almost like 0 to 19, and again this is like 2 to 19%. So this is the analysis hours. When the general one is taking almost like 50-55 hours, so EPM analysis we're taking almost like 20 hours, so for each one. So this is CPU time. So for different configurations of this is for the L building. So similarly we have done that for the other two things also. So critical time step also been observed. So similarly for other two also we have done the with so 4 different EPMs. So this is the different pile configurations. So number of piles were 23 in the first EPM one. In the EPM two, when we divided it into, it was coming around 11.5 and 11.5, which is been equivalent pair has been done, and these are the dimensions of the equivalent pair. So there is a detailed procedure to calculate this. It's not like random. So there's a detailed theory behind this proposed by Paulus. Then what is the effect of substrata characteristics, especially when you have coastal soil, when you have coastal-less soil, or when you have a C5 soil. In geotechnical engineering, the major challenge is with the mixed soil, because our theories are either prescribed or suggested for C soil or phi soil, but we land up something in between in the field. So we want to understand the effect of cohesion and angle of internal friction, especially in the types of response, okay, with the substructure and the substrata. Then different ground motions we have started taking Indian seismic events. Like as I said, Bhuj earthquake I already explained. In addition to that, we want to take two Himalayan earthquakes, that is Uttarkashi and the Chamba earthquake. Then LBD ratio also we want to vary that. So we started aspect ratio also changed from 10 to 50. We modified that and to done the analysis. So this is the soil properties that considered for the study. So as I said, like 3 different soils. Okay, you can see here C5 soil, C soil, and phi soil. Okay, so this is a C5 soil mixed one. This is a C soil, and this is phi soil. So this is the bearing capacity, so which we calculated, and of course angle of friction, etc. So for these 3 different soils, again different layer, C soil overlain on the phi soil, or like in between C5 soil. So a lot of different combinations we do get in the real field. So what we have started firstly was like, let's take a homogeneous data. Okay, if you start building something in a marine environment like Kochi or somewhere, you will get a very homogeneous, clay formations, especially in the coastal areas. So what we started looking at is like how these, okay, first let's see with homogeneous data of C5 and C5 under different asymmetry, and how the overall response of the system behave. So this is for 3 different soils, phi soil, C5 and C soil. So building response, and this is the substructure response, and X and Z directions at top, center, and bottom. So similarly for superstructure also at different nodes. So what we observed is like in almost all the 3 different soil types, C1s are giving higher response when compared to the LNT. So then like the overall displacements in almost all the 3 different buildings for 3 different soils were ranging from 12 to 15%. That is the displacement variations. And whereas the C-type soils shows more transfer of vibrations when compared to phi and C5 soil. This is one of the interesting observations. And another one has been like, same observations we can also find the other asymmetrical structures of C and T as well. And C response was higher when compared to L and T. So for almost all 3 different type of soils, and the response of the foundation system, it's ranging from 4 to 9% overall in almost all the 3 different asymmetrical structures supported by 3 different type of soils. Then other the thing that we want to do is like how the ground motion effect of ground motions, okay, either far field or near field effects, to understand that, because that's one of the interesting or complex thing to understand. So as I said, like we have taken 2 Himalayan earthquakes, Chamba and Uttarkashi events, which are very predominant earthquakes that happen, and then of course our Bhuj earthquakes. So these were the ground motion characteristics of the input ground motion that we considered for the analysis. Again, for three different ground motions, we have done the analysis. You can see this is the response for three different ground motions considered. And then later, 2015, when we got Nepal earthquake, we have done that as well. And that part I didn't put it in the slides, but it is published in Journal of Asian Earth Sciences, one of the top journals. Okay. Anyway, so this is actually the response of Chambas, Uttarakashi, and Bhuj earthquake for of both superstructure. This is the superstructure part. This is the substructure part, and for different asymmetrical structures of C, L, and T at different locations or the nodes. So based on this analysis, what we observed, of course, every earthquake, you cannot compare two earthquakes of same magnitude also, because earthquake is not just, comparable with magnitude. There are different other characteristics of this seismic input ground motion. So like, frequency parameters, amplitude parameters, there are different parameters. So no two earthquakes of same magnitude can also be duration parameters. So no two earthquakes of same magnitude can be compared as well. So what we understand, what our goal was like to understand the effect of far field and near field, okay, on the overall response of the superstructure. Because as I said, like when you have Bhuj earthquake, Ahmedabad, which is having 200 kilometers away from the epicenter, had much severe damage than the structures which are near to the Bhuj, very near to the in the Kutch region. So that is like far field effects has to be properly quantified. So the same observations we also made it for three different asymmetrical structures for its peak response. And what we observed is for almost all the earthquakes, C buildings are showing the higher response with respect to. So that means like rather than the far field and near field effect, the building asymmetry is a major crucial controlling parameter for its stability. Then we started looking at the aspect ratio, L by D ratio of the piles. Okay, so we changed because geotechnical design is not like a structural design, right? It requires a lot of creativity, and we need a lot of common sense also. It's not a prescribed design like structural design, right? So because the soil we are handling with a material, natural material, which is for going to take the final load. My superstructure is not taking the load. My substructure foundation is not taking the load. My foundation is a transferring element to the substrata. So finally, the load-bearing element is my soil. Okay, and which is not continuous like your steel or concrete. It is like particulate. So which is a highly dynamic and non-linear. So when you do the pile design, if you give two people the same structure for design or foundation, they come with different solutions. Okay, you have, as I said, there is no prescribed design, okay, for geotechnical structures. So when we look at this one, so people generally go with different pile diameters and something like that. So that's why we want to see in terms of aspect ratio. So which we varied from 10 to 50 like this, and again started the analysis to understand the lateral displacement. So for different L by D ratios. Okay, if you see here for higher L by D ratios, the displacements observed at almost all the story heights was higher. So that was an observation which we could make it for almost all the three different asymmetrical structures. So for large diameters, the displacement found to be less. That means as the LBD ratio was higher, the displacement was higher. And the pile length in contact also contribute to the development of the contact displacements. So that's the soil pile interaction, they contributing in the overall response of the structure as well. Least response was observed for the low LBD ratio, and of course higher was the higher LBD ratio. The system response was almost like found to be 32% higher for C-type asymmetrical structures when compared to the other two L and T, which is higher percent. 32% is much higher. So with all this analysis, like to just conclude, so whatever the numerical tool that has been developed was very effective, and it is considering almost every every aspect of the DSSI. So that code was in good agreement with experimental and the numerical, and the effect of interaction in the analysis, it alters the complete system characteristics, that is to complete superstructure characteristics and its response. The response of this overall system, that is asymmetrical structure, supported on pile raft, is completely different from the symmetrical configuration, especially the degree of asymmetry that is associated, which we consider here geometrical asymmetry. It is having controlling the response of the system, of the building of the same configuration of the same area for same serviceability also. So the EPM model, which we incorporated in our numerical model, so that we can improve the computational time, the efficiency of the computational time. So it was competitive, and the interface effects can be made robust in the CPM model, because you don't need to model 20 different piles. Instead of that, you can have only one single EPM, and the accuracy of this is acceptable in terms of its displacements, what we observed, and earthquake characteristics and the characteristics of substrata, that is soil, in the foundation geometry, they are playing important role in the overall system response. So this, thank you so much for giving this opportunity, especially thanks to Dr. Aruna, who have been, keen to have my lecture. Thank you.
Yes, thank you very much, madam, for sharing your expertise in this field. Any questions from the participants? Please ask, or you can type in the chat box also. Any questions, please? There is one question, madam. How to model the dynamic behavior of soil using linear springs? Hello. There is one question, madam.
Sorry, I just muted it, and I didn't realize that I was in mute. Okay, I was
Yes, sir.
talking, and
There is
yeah,
one question. How to model the dynamic behavior of soil
exactly.
using
Yeah, I
linear
was just
springs?
seeing the question now. One second. So, as I showed you in one of my, modeling details, when I showed you that what we have considered is like we have taken the dynamic soil properties only when we are modeling it. Okay, and we have taken the soil models available. We have used the constitutive soil model. Okay, so as I said, like for soil, we didn't use it as like a linear spring here. What we have taken is like history's model of the soil we have considered and inbuilt in the numerical model. Hello, am I clear?
Yes, madam.
Yeah,
Screen is not visible. They are saying. I
yeah,
think
yeah. I think
you might have stopped sharing.
Yeah, I stopped sharing because I'm done so that I can see the participants. My camera is not working, so that's why I stopped.
Okay,
You
okay.
want anything from my
Any questions, please?
I think I can see the chat box here. Ankit asked this. Mr. Ankit, is that clear? Hello.
Yes, he is replying on chat box. Yes,
Okay,
ma'am.
no issues.
There is one more question by Mayur More.
Effect of dynamic properties. Obviously, right? Mr. Mayur, soil is the only element which is taking the overall load, not your beam column or my foundation. And soil behavior in dynamic thing is something which you must if you want to do SSI. See, low frequency, high, as I said, like, earthquake is very unique. Each earthquake is very unique. Okay, it has amplitude parameters, frequency parameters, and duration parameters. So there are like, low frequency events because of resonance and other things, we don't know the structural frequency, right? We have earthquake frequency, we have a soil frequency, that is the ground frequency, you have the superstructure frequency, right? It's not just only one frequency, earthquake frequency you are considering. When you have a facility, see your client approach you, ki, I want to build a structure of this much, a 10-story, assuming in particular, maybe in an area called Gurgaon. Okay, so 10-story structure, it has its own building response, right? Frequency types. So earthquake frequency, whether you consider whatever ground motion, and then you have to evaluate the ground, that is the soil frequency also. Okay, there are ways of evaluating that. We do microtremor test in the field where you can find out the frequency of the ground. It's also material, right? Soil is a material. It also have a frequency. So it's all the three elements has to be properly modeled. What should be the spring stiffness for black cotton soil for modeling FEM? Please read this. This is a basic thing. Okay, I don't have any exact details, but you have to calculate that. During poor ground condition of soil, what will be the situation during poor ground? What do you mean by situation? I don't understand. Shubha Katriji. Uh,
Yes,
in,
ma'am. Yes,
in,
ma'am.
yeah,
Good afternoon, ma'am.
good afternoon.
So I have to ask about the situation when the poor ground condition is there, like the black cotton soil. Then what will be the affected?
See, poor ground. How do you define that poor ground? Like anyway, you mentioned it is a black cotton soil.
Means,
For
yeah,
clay,
yeah, yeah.
so as I said in one of my slide, also clays has they were observing higher vibrations.
Higher
So
vibrations.
when we model that completely sea soil, five soil. So in soil, what happens is like the behavior of soil, especially under dynamic load. If you do a cyclic triaxial or resonant column test, okay, under
Yes.
different kinds of soils, especially five soil, C5 or sea soil, the response
Yes.
is very different for everyone, every different soil. Okay, so that dynamic response or the ground response analysis, you have to perform it properly. For alluvial soils, yes, we do have other geohazards, including liquefaction, sand boils. All these things can occur. But in sea, this kind of clay soils, you may encounter with a lot of settlements, like a huge amount of settlements can come in. We don't have the issues of pore pressures or the liquefaction, but you do have severe settlement issues.
Okay, ma'am. Thank you so much, ma'am. Thank you.
Thank you. I left my email ID. If there is anyone who is interested to have any sort of collaboration, you can feel free to write to me. I don't know if we have a QIP program. Okay, so if anybody college teachers are interested to do PhD under QIP, if your institute is allowing, I'm not sure that it needs that QIP from the institute level. If the institute is sponsoring you, you are free. Even from industry also, you can come as a sponsored PhD student, sponsored category. Okay, so and for master students and undergraduate students, so we have internship program. You can check it from the IT Indore website. So if you are interested, you can contact the concerned faculty with whom you want to work, and you can. That's one of the active internship programs we do have at IT Indore now. Okay. Dr. Anna, anything?
Yes, madam. I think so. There are no questions. Thank you very much, madam, for sparing your
Thank you.
time and giving the expert talk in the ATAL FDP program. Thank you very much and hope your guidance in future also.
Yeah, thank you so much. Thanks to all participants for the patient listening. Thank you, Arna. Thank you.
Thank you. Thank you very much.
Okay.
So we are leaving the
Thank you, ma'am.
uh, for the lunch break. We will meet again at 3 p.m. for the last session. Thank you very much, all the participants.
Thank you, ma'am.